Every night, as we gaze up at the star-filled sky, do you ever wonder, where do those glittering points of light come from? How do they live, and what will their ultimate fate be? Far from being mere static points of light, each star is a miniature universe, carrying within it a dramatic story of birth and death, spanning millions, even billions of years. From colossal clouds of dust and gas to moments of glorious explosion or quiet demise, the life of a star is the universe's grand symphony. Today, we will embark on that extraordinary journey together, from when a star is born, shines brightly, until it closes its eyes forever, leaving a legacy for future generations of celestial bodies. Get ready for a journey through time and space, where the life and death of cosmic giants are revealed. Welcome to SpaceTime's universe journey of discovery, where we explore the deepest mysteries of the universe. In this video, we will explore the life of the stars, from forming to fading. Don't forget to subscribe to the channel so you don't miss out on other exciting universe exploration videos. If you find the video interesting and useful, please like and share to support us.
Our universe is not an infinitely empty void. Rather, it contains magnificent structures of gas and dust, radiant and mysterious nebulae. In the vastness of interstellar space, there exist giant molecular clouds, stellar mercuries composed primarily of hydrogen and helium, along with a small amount of heavier elements, the cosmic seeds for all subsequent life. These clouds, with their mesmerizing beauty, are where the life of a star begins. Within these vast nebulae, which can span hundreds of light years, the density of matter is very low, but not entirely uniform. There will always be regions with slightly higher densities compared to their surroundings. It is these seemingly insignificant tiny density fluctuations that serve as the initial cradles for a star's formation. Under the relentless influence of gravity, gas and dust particles in these denser regions begin to attract each other, pulling them closer together, forming an increasingly dense clump of matter. This process of gravitational contraction does not happen chaotically. As the cloud of matter shrinks, it begins to spin faster due to the law of conservation of angular momentum. This contraction and rapid rotation increase the pressure and temperature within the cloud's core. Initially, the heat generated easily escapes as infrared radiation, allowing the cloud to continue shrinking. However, as the density and temperature in the core reach an extreme threshold, the core becomes dense enough to trap most of the heat. At this point, the internal temperature rapidly skyrockets, and the cloud begins to glow intensely, primarily in the infrared spectrum. At this stage, we call it a protostar. The money continues to smoke materially from the cloudy cloud. The protostar continues to accumulate matter from the surrounding nebular cloud. The protostar's energy primarily comes from the release of gravitational energy as matter falls into its core. The protostar stage can last from a few 100,000 years for massive stars to several million years for more modest-sized stars. Throughout this period, even though it is glowing and hot, a protostar is not yet considered an official star. This is because the temperature and pressure within its core are not yet extreme enough to ignite nuclear burning, the fusion of hydrogen into helium, the true lifeblood of all stars. It is a promising gestational period, preparing for a brilliant life to come. The grandest moment in a star's life is when it truly ignites. As the protostar continues to contract and the temperature at its core reaches an astounding threshold, approximately 15 million degrees Celsius, coupled with immense pressure and matter density, the ideal conditions for a cosmic miracle are set. Under these extreme conditions, Hydrogen nuclei, accelerated to extreme speeds, begin to collide with enough force to overcome the enormous electrostatic repulsion between them. This is nuclear fusion, a world-shaking elemental transformation process where 4 hydrogen nuclei merge to form one helium nucleus, releasing a colossal amount of energy, according to the famous equation E equals mc squared. This burst of energy is the star's life source and its heart. The immense energy released from nuclear fusion creates a powerful outward pressure, a continuous push that counteracts the relentless collapse of gravity attempting to pull matter inward. When these two opposing forces reach a perfect equilibrium, the star enters the most stable and longest phase of its life, known as the main sequence. Our Sun, the star that nurtures life on Earth, is currently in the middle of this main sequence phase, having shone steadily for approximately 4.6 billion years and is expected to continue for another 5 billion years. The lifespan of a main sequence star is entirely determined by its initial mass. It may seem paradoxical, but the larger, more brilliant, and impressive stars have shorter lifespans. The reason lies in their enormous mass. The gravitational force in the cores of these stars is many times stronger, requiring significantly higher temperatures and pressures to maintain equilibrium. This leads to an incredibly rapid rate of hydrogen fuel burning, like a race car consuming fuel quickly to maintain maximum speed. For example, a star 10 times the mass of the Sun might only live for a few tens of millions of years, a blink of an eye on the cosmic timescale. Conversely, a red dwarf star, with only 1/10 the mass of the Sun, can sustain hydrogen nuclear fusion in its core for hundreds of billions to trillions of years.
This period is longer than the current age of the universe, meaning the first red dwarf stars are still alive and will continue to exist long after our Sun has faded. During the main sequence phase, the star maintains a relatively stable size, luminosity, and surface temperature, acting as a steady beacon in space. Everything has an end, and stars are no exception. When a small or medium-mass star, like our Sun, exhausts its precious hydrogen fuel in the core, the nuclear fusion process at the center ceases. This cessation means the loss of outward radiation pressure. With no opposing force, the star's core, now primarily helium, begins to rapidly contract under the relentless squeeze of gravity. The core's contraction triggers dramatic chain reactions. As the core shrinks, its temperature and pressure rise significantly, enough to ignite a new process. Hydrogen fusion no longer occurs in the core, but begins to intensely operate in a thin shell surrounding the contracting helium core. This shell hydrogen fusion releases an enormous amount of energy, much more powerful than before. This energy pushes the outer layers of the star to swell and expand, sometimes up to hundreds of times its original size. As the outer layers of matter expand away from the core, they simultaneously cool significantly, causing the star to turn a brilliant red and become terrifyingly large. At this point, the star is called a red giant. The size of a red giant can be so immense that it swallows the inner planets of its system. For the Sun, it will expand and engulf Mercury, Venus, and possibly even our Earth. This is a distant but inevitable prospect, a final chapter in the life of the star system we inhabit. However, the life of a red giant is not the end. For stars similar in mass to the Sun, when the helium core continues to contract and heat up, it becomes extremely dense and reaches a temperature of approximately 100 million degrees Celsius. At this temperature, a new nuclear fusion reaction is ignited. Helium begins to fuse into carbon and oxygen through a series of reactions known as the triple alpha process. In some special cases, for stars with a degenerate helium core, this helium fusion process can begin abruptly and extremely explosively, an event known as a helium flash. After this flash phase, the star will reach a new equilibrium state and stabilize briefly on the horizontal branch, continuing to fuse helium in its core. But the helium fuel source is also limited. After the helium in the core is completely exhausted, the star's core once again begins to contract, now a carbon-oxygen core. Helium fusion will move to a shell surrounding the carbon-oxygen core, and hydrogen fusion will continue in an even more outer shell. The star swells up once more, becoming even larger and brighter, entering the asymptotic giant branch phase. This is one of the final and most unstable stages in a star's active life cycle, where matter from the outer layers is expelled into space in the form of fierce stellar winds. These stellar winds carry away the outer layers of the star, completely detaching them from the core's gravity. This matter, consisting of gas and dust, forms a radiant and complexly structured cloud around the star's shrinking core. This is a planetary nebula. The name comes from 18th century astronomers who saw them through telescopes and mistook them for faint, round disks resembling the planet Uranus. Planetary nebulae often have incredibly diverse and beautiful shapes, existing for a few tens of thousands of years before dispersing and merging with interstellar space. After the star's outer layers have completely detached, the remaining core is a tiny, extremely dense and hot object, mainly composed of carbon and oxygen. This object is called a white dwarf. A white dwarf no longer has enough temperature and pressure to perform any nuclear fusion reactions. The pressure resisting its further contraction comes from a quantum mechanical phenomenon called electron degeneracy pressure, arising from the Pauli exclusion principle. White dwarfs gradually cool over an extremely long period, billions of years, radiating their remaining heat into space as faint light. They are the final outcome of about 97% of stars in the Milky Way, including our Sun, after approximately 5 billion years. Eventually, after a sufficiently long period, perhaps trillions of years, a white dwarf will cool completely. It will no longer emit any significant light or heat, becoming a black dwarf. Black dwarfs are theoretical objects. We have never observed them, simply because the universe is currently still too young. They are cosmic ghosts, cold and dark relics of a brilliant past. While small and medium-sized stars end their lives relatively peacefully, the fate of stars with initial masses many times greater than the Sun, typically more than 8 solar masses, is entirely different. Their lives are more dramatic and violent, leading to some of the most spectacular cosmic events. After exhausting hydrogen in their cores, they also expand, but not into red giants, but into red supergiant stars. These supergiant stars are truly enormous in size. If placed in the Sun's position, they would engulf the entire orbits of inner planets like Mercury, Venus, Earth, Mars, and might even extend beyond Jupiter's orbit. The extreme temperatures and pressures in the cores of these stars allow them to fuse heavier elements after helium. Nuclear fusion occurs in layers, forming a gigantic cosmic onion-like structure. In the outermost shell, hydrogen is still fused into helium. Inside that layer, helium is fused into carbon and oxygen. And so on, in deeper and hotter layers, heavier elements continue to be produced. Carbon into neon, neon into magnesium, magnesium into silicon, and finally, silicon is fused into iron right at the star's core. Each of these shells corresponds to a different type of nuclear fusion reaction, each reaction requiring higher temperature and pressure than the previous one. Iron is a special element and the destroyer in the stellar nuclear fusion process. When the core of a supergiant star becomes entirely iron, the energy-producing nuclear fusion reactions abruptly cease. The reason is simple. Iron fusion
does not release energy. On the contrary, it requires energy to occur. This means the iron core no longer produces outward pressure to counteract the tremendous gravitational force. In a fleeting moment, billions of tons of iron core material suddenly lose support from radiation pressure. In less than a second, the iron core collapses extremely rapidly under its own gravity. Matter is compressed to an unbelievable degree. Protons and electrons in the core are squeezed so intensely that they merge to form neutrons, releasing a large number of neutrinos. This collapse occurs at astonishing speed, up to 70,000 kilometers per second, equivalent to about 23% of the speed of light. When the core collapses to the density of an atomic nucleus, the densest and most unimaginably dense matter in the universe, it abruptly halts and bounces back violently, creating a colossal shockwave. This shockwave rushes outwards, tearing apart the remaining layers of the star in the most horrific and brilliant explosion the universe can create, a supernova.
A supernova explosion can outshine an entire galaxy for a short period, just a few weeks or months, but it releases energy equivalent to what the Sun produces over its entire 10 billion-year lifespan. These are rare but incredibly important cosmic events, the factories that synthesize and disperse most elements heavier than helium in the universe. Carbon, oxygen, nitrogen, the basic elements for life, along with iron, gold, silver, and uranium, all are created and dispersed into space by these supernova explosions. We, our bodies, and everything on this Earth are truly made of stardust, the remnants of stars that died billions of years ago. After the dazzling supernova explosion, not everything disappears. What remains is the remnant of the original stellar core, and its fate depends entirely on its mass. If the remaining core has a mass of about 1.4 to 3 times the mass of the Sun, it will collapse under immense gravity and become a neutron star. Neutron stars are one of the densest objects in the universe. They are a sphere only a few tens of kilometers wide, but many times heavier than our Sun. A teaspoon of neutron star matter can weigh billions of tons. They rotate very quickly, have extremely strong magnetic fields, and sometimes emit powerful beams of radiation periodically, known as pulsars. However, if the remaining core after the supernova explosion has a mass greater than about 3 times the mass of the Sun, even neutron degeneracy pressure cannot overcome gravity. The core will continue to collapse endlessly past the Tolman-Oppenheimer-Volkoff limit until it becomes a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it has crossed its event horizon. We cannot directly see black holes because they do not emit light, but we can detect their existence through their tremendous gravitational effects on surrounding stars and matter, as well as the X-ray radiation emitted as matter is drawn in. Black holes represent the most extreme end of a star's life cycle, where everything we know about physics seems to be bent to its limits. Whether white dwarfs, neutron stars, or black holes, all these remnants, along with the gas and dust blown out from planetary nebulae and supernova explosions, are not a permanent end. On the contrary, they are seeds, raw materials for subsequent generations of stars. Matter, rich in heavy elements, created in the cores of stars and dispersed by their deaths, will merge into new gas and dust clouds in the galaxy. This process facilitates the formation of new generations of stars, the planets orbiting them, and even the emergence of more complex life, like us. This eternal cycle is a powerful testament that death in the universe is not a complete cessation, but an essential part of continuous rebirth, evolution, and renewal. Every star that dies allows thousands of other stars to be born. And so, we have witnessed the magnificent entire life cycle of a star, from its primordial beginnings in cosmic mists to its transformation into mysterious celestial relics.
Every star, whether large or small, brilliant or fading, contributes to the universe's richness and diversity. But all these stars, along with our planet and countless other celestial bodies, are part of a grander structure, a galaxy. In the next episode, we will delve deep into our galaxy, the Milky Way, and its unexplored secrets. We will learn about its strange structure, its mysterious central stars, and our small but significant place in this vast universe. Don't miss it.